Volcanic activity can replenish planetary atmospheres, and for planets with strong magnetic fields, such atmospheres are less likely to escape. However, since we lack information about Proxima B's volcanic activity or magnetic field strength, we cannot speculate on whether the planet has an atmosphere. An atmosphere suggests the presence of bodies of water, which in turn implies the potential for life. This raises our curiosity about whether Proxima B might host a sophisticated civilization that utilizes solar panels on its dayside to generate electricity, which could be crucial for illuminating and warming the night side, typically too cold and dark for comfortable living. The discovery of Proxima B has sparked a race to determine whether it crosses its star's face as observed from Earth. Such transits would allow scientists to measure the planet's size and mass, thereby enabling them to assess its density and confirm its rocky composition. During a transit, starlight may reveal details about the planet as it passes through its atmosphere. However, the alignment necessary for scientists to observe a transit is only about 1.5%. Additionally, the star's tendency to flare adds complexity to the situation. As astronomer David Kipping from Columbia University explains, the star's heat causes rocky planets to absorb sunlight and re-emit it as infrared radiation. Nevertheless, rocky planets emit a distinct type of infrared radiation compared to stars like Proxima Centauri. Moreover, the James Webb Space Telescope, JWST, was specifically designed to study infrared light, which is crucial for identifying Proxima B's heat signature. This infrared data will be instrumental in detecting any atmosphere the planet may have. Interestingly, the JWST could potentially identify city lights on Proxima B's night side, even if they are as dim as those currently used on Earth, as long as the illumination is confined to a frequency band that is 1,000 times narrower than the light from the star. Proxima B's dayside might be extensively covered in solar panels, reflecting starlight, and since the planet has a synchronous rotation, its day and night are the same length, with cool evening temperatures following daytime highs. The temperature difference between the day and night sides, however, is influenced by whether the planet is solely composed of bare rock or has an atmosphere and oceans, which both conduct heat. If there's no atmosphere, the temperature disparity between day and night would be greater. In fact, since the day side would emit all the energy it receives from Proxima Centauri as a black body, we can calculate the precise amount of black body radiation expected. Conversely, the night side would appear extremely cold and inhospitable. If the temperature difference is minimal, it suggests the presence of an atmosphere. Fortunately, the JWST can measure the infrared radiation from Proxima B's two sides in just 11.2 Earth days after completing its orbit around the star. If Proxima B possesses an atmosphere, the next step would be to analyze its composition. The presence of gases like oxygen, water vapor, and methane could indicate habitable conditions or even the existence of life. However, capturing starlight as it interacts with the planet's atmosphere is a challenging task. The JWST can only closely examine a limited number of nearby potentially habitable worlds because it was not specifically designed to search for extraterrestrial life. Furthermore, it can only track changes in the concentrations of gases like methane, carbon dioxide, and water vapor, but it cannot detect unbonded oxygen, which is the most reliable indicator of life. One of the planned ground-based observatories, the Extremely Large Telescope, is expected to start operations in the mid-2020s and may be capable of conducting more comprehensive atmospheric studies, including the detection of ozone. Until these telescopes become operational, the JWST may provide valuable insights for at least a decade. Future space telescopes could employ advanced techniques to obscure the brilliance of a planet's host star, making it easier to study the light reflected off the planet. This is similar to covering a light source with your hand to improve visibility of distant objects. Such telescopes might utilize small internal masks or large umbrella-shaped satellites to block starlight, thus facilitating the examination of reflected light from the planet. Unfortunately, many gases associated with life on Earth can also arise from non-biological processes. For instance, both cows and volcanoes produce methane, and sunlight can split water molecules into oxygen and hydrogen through photosynthesis. As astronomers search for signs of alien life, they may encounter numerous false positives, making it imperative to have a thorough understanding of a planet of interest to differentiate between geological or atmospheric processes that might resemble a biosignature and eliminate false indicators. The next wave of planetary research could yield compelling evidence for the existence of life beyond Earth. Preliminary data from the James Webb Space Telescope offers a glimpse into the significant advancements that lie ahead. The question of whether life exists elsewhere in the universe is one of science's most pressing inquiries. It is conceivable that life is abundant throughout the cosmos, or we may find ourselves entirely alone on this solitary planet in the vastness of space. In either case, profound philosophical and psychological adjustments may be necessary among people when the eventual resolution emerges. The quest for extraterrestrial life has fascinated humanity for centuries, inspiring countless stories and theories. As our technological capabilities advance, our understanding of the cosmos grows, unveiling new possibilities for life beyond Earth. The deployment of space telescopes like the JWST not only enhances our ability to detect distant planets but also enables detailed analysis of their atmospheres, aiding scientists in identifying potential biosignatures. Furthermore, the exploration of exoplanets fosters collaboration within global scientific communities, enhancing knowledge sharing and resource pooling, which increases the likelihood of significant discoveries. These collaborative efforts also boost public interest and engagement in space exploration, as findings are often shared with a broad audience, igniting curiosity and imagination. Additionally, the philosophical implications of discovering life elsewhere prompt deep reflections on our existence. Would the discovery of alien civilizations alter our understanding of life's purpose? Such questions challenge us to re-evaluate our role in the universe and our relationship with our home planet. As we continue to refine our technologies and methods for exploring the stars, each new discovery brings us closer to answering the timeless question: are we alone in the universe? The journey ahead is filled with potential, propelling our quest for knowledge and understanding beyond our earthly boundaries. Renewed by volcanic activity, planets with solid gravitational fields are less likely to lose their atmospheres. However, since we lack information about Proxima B's volcanic activity and gravitational strength, we cannot even speculate about the presence of an atmosphere. An environment typically suggests the existence of oceans, which in turn implies the potential for life. We are eager to find out if Proxima B hosts any form of advanced human civilization. It may have solar panels on its sunlit side to generate power, providing warmth and light to the darker side, which would otherwise be too cold and dim for comfortable habitation. The discovery of Proxima B has sparked a race to determine whether the planet transits its star as seen from Earth. Such transits would allow scientists to measure the planet's size and mass, which would help assess its density and confirm its rocky composition, providing insights into the materials that make up its surface. During a transit, starlight could reveal the planet's characteristics by passing through its atmosphere. However, the likelihood of Proxima B having a transit aligned favorably for observation is only about 1.5%, as the star's propensity for flares complicates matters. Astronomer David Kipping from Columbia University notes that the star is intriguing because stellar radiation allows a rocky planet to absorb sunlight and re-emit it as infrared light. Rocky planets emit a distinct type of infrared radiation when observed from stars like Proxima Centauri. Moreover, the James Webb Space Telescope, JWST, was specifically designed to focus on infrared light. The infrared signature of Proxima B is crucial for determining whether it has an atmosphere. This part of the spectrum is particularly valuable for the JWST, which could potentially detect city lights on Proxima B's night side, even if they are as faint as those used on Earth. The JWST can identify artificial illumination as long as it remains within a frequency band that is a fraction of the star's brightness. The daytime side of Proxima B might be heavily equipped with solar panels reflecting sunlight, while the planet constantly rotates, leading to significant temperature variations between day and night. The extent of this temperature difference depends on whether the planet comprises exposed rock or has an atmosphere and oceans, both of which can regulate heat. If there is no atmosphere, the temperature disparity between day and night would be more pronounced, as the day side would radiate almost all the energy it receives from Proxima Centauri as a black body. Consequently, the night side would likely experience severe cold. Conversely, if Proxima B has an atmosphere, the temperature variation between day and night will be less dramatic, suggesting the presence of an atmosphere. The JWST can measure the infrared radiation from Proxima B's two sides over a period of just 11.2 Earth days after completing its orbit around the star. If Proxima B does have an atmosphere, the next step would be to analyze its composition. The presence of gases like oxygen, water vapor, and methane could indicate habitable conditions, if not direct evidence of life. Achieving this requires capturing starlight as it interacts with or passes through the planet's atmosphere, a challenging task. Although the JWST was not designed specifically to search for extraterrestrial life, it can monitor changes in the atmospheric concentrations of methane, carbon dioxide, and water vapor. However, the JWST cannot detect unbonded oxygen, the strongest indicator of biological processes, even though certain combinations of these gases could suggest life. Ground-based observatories, such as the extremely large telescope set to begin operations in the 2020s, will also be able to conduct detailed atmospheric studies. Ozone might be one of the substances that the JWST can detect. Until those ground-based telescopes are operational, the JWST could provide valuable information for the next decade. Future space telescopes may utilize advanced methods to obscure the overwhelming brightness of a planet's host star, allowing astronomers to observe reflected light from the planet itself. This approach could be similar to covering a light source with your hand to see distant objects more clearly. Advanced space telescopes might employ small internal covers or large, umbrella-like external shields to block starlight, making it easier to analyze the light bouncing off the planet. Unfortunately, many gases produced by terrestrial life can also be generated through non-biological processes. For instance, both cows and volcanoes produce methane, and sunlight can break down water molecules into oxygen and hydrogen via photosynthesis. Consequently, astronomers searching for extraterrestrial life must navigate the potential for false positives, necessitating a thorough understanding of a planet's characteristics to determine whether its geological or atmospheric processes might mimic biosignatures, helping to rule out false indications of life. The next wave of planetary exploration could yield compelling evidence regarding the existence of life beyond Earth. The JWST's primary data may offer insights into the significant changes on the horizon. If life exists elsewhere in the universe, it represents one of the most pressing questions in science. It's possible that life is abundant throughout the universe, or conversely, that we are entirely alone, confined to a solitary planet in vast space. Either scenario could lead to profound philosophical or psychological shifts among humanity, as the quest for extraterrestrial life has fascinated people for centuries, inspiring countless stories and theories. As we advance technologically, our understanding of the universe expands, revealing further possibilities for life beyond Earth. The utilization of space telescopes like the JWST not only enhances our ability to identify distant planets but also allows for detailed studies of their atmospheres, helping scientists identify potential biosignatures. Moreover, the exploration of exoplanets fosters collaboration among global scientists and space research organizations, encouraging data sharing and resource pooling, thereby increasing the likelihood of significant discoveries. These collaborative efforts also enhance public interest and engagement in space exploration, as findings are often shared with a broad audience, igniting curiosity and imagination. Furthermore, the philosophical implications of discovering extraterrestrial life could profoundly influence our understanding of life's purpose, compelling us to re-evaluate our role in the universe and our relationship with our home planet. As we continue to refine our technologies and strategies for exploring the cosmos, each new discovery brings us closer to answering the age-old question: are we alone in the universe? The journey ahead is filled with potential, driving our quest for knowledge and understanding beyond our terrestrial confines.